Hello everyone, my name is Numan Iqbal, and in this lecture we are going to learn inside the Comsol Multiphysics how we can calculate the volume of a 3D domain or area of a boundary or surface and length of a simple line or edge. So let's start. In a heterogeneous model, this is a built-in example. If we see over here, there are if we see over here, this is actually a battery model. This is called a heterogeneous lithium-ion battery model. One side, these particles belongs to a cathode or a positive electrode, and these particles belongs to a negative electrode. Okay, we can say the anode. We can see these things over here. This is a negative electrode particles, and this is positive electrode particles, and these we can actually define these kind of things inside the geometry to make all those things like a one domain. Okay, if we do not define these things, make a selection of these things, then these particles will be like I believe these are 32 particles. Each particle will have it's going to say it's one domain. Each particle is one domain. Okay, if we are not going to define these things. Anyhow, our goal is to calculate the area, length, and volume of specific things, and how we can actually do those things over here. Let's start. And yeah, so let's say this is the negative electrode, and we want to calculate its volume of all the particles, and then we are going to say maybe what is the size of one particle. We can calculate that one as well. So over here we are going to define a non-local coupling parameter, where this is the integration. And in the integration, we if we select domain, if I hide this one, okay, so we can select this whole domain. Okay, or we can select from these selections. We have already made these selections inside the model. Then we will select a negative electrode. Now if we apply this integration operator over here, it's going to calculate the properties for this whole electrode. Okay, for all the particles, it's not for just one particle. If we go to the variables, then type like maybe the volume. Okay, volume of negative electrode particles. Okay, you should keep in mind, you have to write component 1, because it's in component 1, sometimes it's model 1, mod 1, so you have to write that name. And then you have to go to the in top 1, where you have defined this thing. You see, in top 1, if it is in top 2, in top 3, you have to write that integration parameter. Okay, the name of that parameter. So it's volume. Okay, we can see it's like units is meter cube. We know that it's volume. Again, let's calculate the surface area of all of these particles. Surface area. If we go to the again non-local coupling parameters, go to the integration, select the boundary this time, and negative electrode surfaces. So it will select all the boundaries of this one. And if we go over here and say area, this is going to calculate the surface area of all those particles. Component 1, in top 2, 1, Okay, we are just writing 1 over here, so it's going to give us either volume, area, or the length. Again, if I make another local parameter, and let's say if uh, unhide all these things, let's say I want to calculate the length of this whole electrode. Okay, maybe if our electrode is just a negative electrode, we can say the length from the separator or the current collector. It's up to you. Okay, so this is the edge, and if we go over here and write the length, again component 1 dot in top 3 1. So now it's going to give me length of this whole edge. First one is the volume of the negative electrode particles, then area, surface area of these electrode particles, and the length. So this way, if you change the domains over here, if we have selected only one particle, if we did not make any selections, we can access all those particles over here, and it will show a lot of domains. Okay, if we do that one, so we can actually select each particle and calculate its volume. Okay, next we can also calculate the surface area if we have selected the boundaries, and if we have selected the edges, we can calculate its length. And of course, if we go to the study, there is no geometric nonlinearity. It means the volume is not being changed. Okay, if it's unchecked, so its volume is not being changed. And also there is I believe in this model there is no volume expansion in this study, but in expansion and stresses there is a change of the volume. If we compute, if its volume is not being changed, so we just have to make a very initial, if yeah, for few time steps, we are going to see if it's giving us solutions. We are going to stop and calculate all those things, because those are not going to change for the later time periods. So it has actually calculated for 0. Now if I stop this one and go to the, these are the derived values. Now other things, what could I do? I could also define the prop values and calculate those things. And other way, I can define the global evaluation, and here I will write volume. It's going to give me volume, area, and length. If I select evaluate in the new table, now we can see, and this is the volume of the negative electrode particles, this is the surface area of the negative electrode particles, and this is the length of this whole surface, the edge. Now what we can do is, if we want to calculate, let's say if we want to calculate the, let's say if we want to calculate the radius of one particle. We know that there were actually 32 particles, and let's assume all these particles are spherical. Let's assume you can also calculate the volumes using this method for the ellipsoid particles, I think. So if these are 32 particles, it means 32 multiplied by 4 by 3 pi r cube. That would be the volume, total volume of all the particles. Okay, so if you do like this, is 32 divided by 4 pi raised to power 1 by 3. I think like this you will be able to calculate the radius, right? I think this 32 should be down. Yeah, 32 4 pi, 32 4 pi, volume multiplied by 3 raised to power 1 by 3. So this way you can calculate the size of one particle. I think it can be beneficial. So if you want to calculate the particle size, average particle size, okay, so you just have to, we already have calculated the volume multiplied by 3 and divided by 4 multiplied by pi and multiplied by 32. One by 3. Okay, so this is going to give us the radius. So rather than using radius, just compute the solution again. Of course, here we are assuming that our particles are spherical. It is just for an example or for a learning purposes. If it's 0 is done, stop. Do the radius, new table, and here we can see it's almost like 0.9 micron or like 1 micron. It's the radius of each particle. Okay, so this way you can use the integration operators to calculate volume, area, length, or maybe the size of the particles inside your models. And you can use this operator to calculate the some kind of accumulation properties. Okay, for example, if there are concentrations, if it is solving for the concentrations, then you just have to calculate the total concentrations, or we can say this is the SOC. Okay, for SOC of whole negative electron particles, we can say in top 1. So this is going to be component 1 dot C. If the variable is C, I think there is no variable C, then we can go and check what is the variable. It should be here. Yeah, this is CS. So if we define CS, it's going to calculate the concentration, total concentrations multiplied by the volume, and if we divide it with component 1 dot in top 1, now we will get the total concentration in one particle. And if we again, if we apply this operator on some other parameter, which can be like we are like totaling or taking the summation. So in this way, it's quite good actually to calculate those things. We can also take the average, but I think integration operator is more accurate than the average one. Now if we do our simulation, it's going to tell us what is the SOC or the state of charge of the particle. And if we divide with the C total or maximum concentration, then we are going to get this SOC like in percentage form, or 0 to 1 or 0 to 100%. Okay, I think you understand those things very well. Yeah, any question till here?